What's up, guys? Today I'm doing a different video than every other video I've done because most of the stuff I do involves computers, but today I'm just going to kind of go ahead and explain the brief basics of sub panels and electric power distribution, just because this is the area I started out with many years ago when I started getting into just weird stuff like this. I started out in lighting, stage lighting, sound, and mainly lighting and power like this, power distribution. And I kind of got out of it just because it wasn't, for me, it just wasn't, how do I say it, challenging enough. You know, it became kind of simple, repetitive, same thing over and over again. So, but I started out doing this, and I figured I'd just do a little video on sub-paneling or even main distribution, electrical distribution, for those of you guys who don't know anything about it. So, this is just a Square D QO box. I'm not sure the exact model number of it, but it's just a Square D panel. Back in the day, I would use this for when I had lighting. I had a lot of really powerful lighting cans and stuff that required a large amount of currents. I also did stuff with transformers and stuff for microwave transformers, arcing and stuff like that, which I might do tutorials on that. So I use this. It was right now, it's obviously it's not hooked up or anything. It's just a panel laying here on my bed. But I used big, huge cam feeds like this, cam lock feeds. I don't know if any of you guys are familiar with this, but this is used a lot in entertainment industry, studio, and stuff like that. They're just huge single pole connectors, and these will probably do about 100 amps a piece here. So, you know, you could do a couple hundred amps with connectors like this. I think these ones are only rated to 150, but cam connectors can go up to like 400 or 500 amps a piece, so just depending on the connectors you have. But that's how I was actually powering it. It was never actually permanently mounted, it was just a little portable panel. So to show you guys, the basics of any electrical panel, this is how it'll be for, when you go into your house or whatever, or if you ever want to wire up a panel or ever add a circuit or anything. It's not too hard, and it really isn't too hard to understand, but you do have to know what you're doing. You don't want to go in here not knowing what you're doing. So let's go ahead and take a peek. I'm going to pull the cover off, and there's absolutely nothing in here right now. There's no wires or anything. This used to be full-blown hooked up, like there's wires running through this like no tomorrow. But I don't really do, like I said, I kind of don't do power distribution or anything anymore. I'm more into like technical stuff like servers and computers and stuff, but I know a lot about this, so I thought I'd teach you guys the basics of it. So, this panel here is a 200 amp panel. I have here the main breaker in my hand. So, any sub panel is going to be like this. This is a single phase panel, so it has only 2 hot wires. A 3-phase panel will have 3 hot wires. This is how it's going to look in any house, any sub panel, any main panel that you have. There's really no difference between a main panel and a sub panel. A sub panel is the main panel is where your main feed comes in from the transformer to your house. And a sub panel is just a panel that comes in from your main panel to your sub panel. It's the same thing, really. They are essentially the same thing. Just the main panel is where your main feed comes in. Anyways, you'll have 3 big lines that come in, 3 huge lines. In this case, they're not hooked up, but they would be. In this case, you'd have the white, neutral, and then you'd have 2 hots. In most cases, they're just going to be big black wires that come in, but in this case, it's red and white. And if you had a 3-phase, it'd be a red, white, and black. And then your green is your ground. And usually, the ground is actually ground is a big bare copper cable that'll come in. Actually, usually from the bottom, because it's going to a piece of steel rod going into the ground. It's literally going to the ground. And it's a big copper wire, and it'll go into a ground strip like this on the side, or it'll go into your neutral strip if it's the main panel. I'll get into that in a little bit, but yeah, they're separate if it's a sub panel. I'll talk about that in a little bit. Alright guys, so we're going to do a basic explanation, a little rundown of how it works, okay? So, how everything works is you have your main neutral line here, and then I have, like I showed you, the main breaker is going to slide in right here, okay? So, this is going to be the same for any case, sub panel, main panel, small little home, huge building, no matter what. Like I said, most times you get to a large building, you're going to be dealing with 3-phase. It's no different than this, just a third hot light. But anyway, So you have your main neutral and then your two hot lines, and then from here to here 120, here to here 120, there to there 240. Okay. Now, if you guys don't know what the neutral is, basically it's a 0 volt line, and like in a light socket, if you have a normal 120 volt light socket, on the left side there's a larger prong. That's the neutral. The right side's a smaller prong. That's going to be either one of these two legs, A or B, and then your ground. And your ground is your ground. I'll explain that in a little bit, how the ground works. But yeah, anyways. So I just want to show you guys something here. We'll show you guys a little thing here. When the power comes out of the breaker here, it alternates. So you have this phase, this phase, this phase, this phase, this phase, this phase, and it goes back and forth. Notice if I throw the cover on here, you have the phases marked here. That's the phase symbol, A, B, A, B. So you know which breaker is pulling from what phase, right? So on a typical light socket, you would have a breaker like this. This is just a 20 amp breaker, and basically what happens is, okay, you're gonna have that breaker that's gonna, it's basically, it has a little contact back here. Here's how the breaker works, and it pulls power from this rail coming from this main breaker. So it's gonna pull from this huge bus bar right here, okay, and that's gonna have power going into this breaker from those little teeth back there, okay. Power is going to come out of the breaker through this little screw terminal right here. I don't know how well you guys can see that, but that's where the power exits the breaker and goes to the circuit that this breaker is powering. Okay, so it just pops in there. I mean, this isn't a guide to how to put circuit breakers in, but it's just showing you how it works. Okay, this is a 20 amp breaker, so this is what you'd find in a typical 20 amp circuit. So it's going to pull power from this phase right here, and then it's going to output it through here. So this is going to be 120 volts. And then the other leg is going to have it referenced to this neutral bar. So you're going to have a neutral going to a light socket or a light switch, whatever the hell the case may be. Microwave, dryer, oven, whatever the hell it is. And then that's going to come, it's going to get its power from this screw right here. And it's going to have a maximum capability of 20 amps. And if it pulls more, the breaker trips. Okay. So you would be using the lug up here from the breaker and then the neutral line, right? So that's how that works. So a 240 breaker, I have here a 240 breaker, same exact concept, except it's just two breakers tied together. This is a 60 amp breaker. This would be for something like a large air conditioner or a, a hot tub or something like that. So you have a prong here and a prong here. Okay, we pop it in. And these ones are a little bit more difficult to do, especially with one hand here, and a breaker this size. But you can see here that it has two breakers tied together. So you have 240 coming out there, and it's pulling from this phase and this phase. So it's pulling from both phases. So now you have 240 coming out there, 60 amps, and I'll go ahead and throw the cover on here just so you guys can see. It goes. This breaker is pulling from phase A, this breaker is pulling from phase B right there, alright? So it's pulling from both hot legs. This would run something like I said, an air conditioner or something. If the appliance only needs 240 volts, typically it just has two hot lines and a ground. But sometimes it does have little things inside it that do require 120 volts, in which case you would just have a little neutral go along with it. Sometimes it's a smaller gauge wire because the things that do require 120 volts don't pull quite 60 amps, so that it doesn't need to have that large of a neutral. In that case, you'd have a little neutral that goes along with it, and it would pull 120 volts from either of the legs to the neutral, and the main appliance that pulls the 240 would pull from both hot legs. Alright, so there's one more type of circuit breaker that is found commonly today, and that is this kind. It's an AFCI breaker. So it's typically the same as a normal breaker. It's basically the same as a normal circuit breaker, and we'll go into depth about what this is. So you can find these in any size. This particular one is a 20 amp AFCI. Okay, So, I mean, you can find these in 15 amp, you can find them in 20, 30, 40, 50, 60, probably all the way up to like 100. You can probably find specialty ones that go higher. This is a single pole breaker. You can find them in 2 poles, 3 poles for 3 phase. You can find them in anything, okay? So, basically, we have a 20 amp breaker here, which I discussed earlier. It basically is simple. It has pulls from the hotline and goes out, and it monitors the current. So to explain, let me explain how this works basically real quick. So basically, when you have electric current flowing through here, if you guys don't know, electric current when it flows through something makes a magnetic field. So it actually has a wire in here where all the current passes through, and it actually runs through like a little iron bar and everything, and it overcomes the tension of a spring in here. There's a spring in here, and if it's able to pull past a certain point, there's so much current through there that it's around 20 amps plus or minus a certain percentage. I don't know. It has to be pretty close to be UL listed, but and that'll mean that it's pulling over 20 amps, in which case it'll overcome the tension of the spring and it trips the breaker and breaks the circuit. Okay, so that's how a normal AC circuit breaker works. And then the power obviously comes out your screw here. So it just has the thing going through there, through the magnetic thing, and it is basically just a little piece in your circuit that detects the amount of current through the magnetic field. Same exact thing is going on here. You have your prong there. It goes onto your bus bar and pulls current from there. And then you have your screw, your output screw right there. Okay. The only difference is this also monitors the neutral. So let's go ahead and take a look at it. So normally you would have, okay, let's put up both breakers. Let's see. Okay, normally you have it pulling from the hotline. There's your output hotline, and then you have your neutral coming off your little neutral bar here, your screw terminal. So you have your screw terminal that goes to your circuit, then you have your hot that comes out of your breaker, and that goes to your circuit. Okay. In this case, same thing. Pulls from the hotline. You have your hot that goes to your circuit, but you do not pull from this neutral screw terminal directly from it. You go through the circuit breaker. So the circuit breaker has this wire coming out of it, and that pulls from this neutral screw terminal. And you can see that on the output of the breaker, there's also a silver screw. So there's a silver screw and a gold screw. Okay, and the gold screw is your hot, the silver is your neutral. So the difference is, not only does this breaker monitor the hotline, how much current it's pulling, so it has the same thing for the magnetic wise to monitor current, but it also monitors the neutral line. Now the neutral line doesn't ever pull any current, so that's the thing. So what it does is, if you guys know how a circuit works, typically, you know, if a circuit has power that comes out of your hotline and returns through your neutral line, that's what your neutral line is there for. So it comes from your hotline, goes to your breaker, goes through a light bulb or whatever the hell the case may be. It can go through a million different things, anything that you can plug in, and then it goes back and comes through your neutral line to complete the circuit. That's what the neutral line is for. Okay, these breakers monitor the neutral line. So here's what these things do. There's AFCI and there's GFCI. This stands for arc fault circuit protection. GFCI stands for ground fault circuit protection. Okay. This basically just detects to make sure that there's no arcs going on in the circuit. It also detects to make sure in a ground fault that there's no like ground faults going on where there's water. So if there's a bathtub or something, make sure that there's no electricity flowing through water or grounded circuits, you know. If there is, it'll instantly shut off. So basically, to explain how these work in detail, not too much detail, but just a little bit of detail, there's actually an electronic circuit in here. And what it does is it monitors how much current is coming in from the hotline. So it monitors, let's just say there's 15 amps coming in. And it also monitors how much is going back into the neutral line. So typically they should be the same. You have 15 amps going through your breaker, you're going to have 15 amps going back into your neutral line. It has to be exactly the same. Normally what you have comes in goes right back into your neutral line, right? It's like you turning on a sink. You have all the water that comes out the, for the faucet is all going to go into the drain normally. So what comes out of the faucet goes directly back into the drain. Same thing here. What comes out of this bus bar is going to return through the screw terminal here. Okay. Now, this breaker, since it's monitoring exactly how much is returning through the neutral line, because it monitors the neutral line as well, it finds a difference. So if it finds that there's 15 amps coming in through here, but only 14 amps is coming back in through your neutral, that means that there's an amp of current going somewhere besides this neutral bus bar. That means it's going somewhere that's a grounded circuit, or it's going somewhere else. It's going somewhere where it shouldn't. Okay? So you have 14 amps going through your neutral coming back from that circuit, but you're putting out 15 amps. That's not good. That means there's an amp of current being lost somewhere. This breaker will immediately trip. Now that's a lot of current. An amp is a lot. These breakers typically trip if they detect, 30, 40 milliamps of difference. So if there's, let's just say 13.2 amps coming in here, and then there's only 13.1 coming back to this neutral. This breaker would immediately detect that 0.1 amp, and it would shut off immediately. And basically that's just to, a safety measure to see that there's 100 milliamps of current being lost somewhere. That could be an arc, that could be, a ground fault, it could be whatever. Ground faults are a lot more sensitive. They're about 5 to 10 milliamps. So if they detect 5 milliamps of current that's not coming back through this neutral line, they shut off immediately. That means it's going through the ground line. Okay, so that's the difference between those. These just detect how much current is flowing. They don't care where it comes back through. They don't care if it goes to the ground. They don't care if it goes anywhere. They just care how much current is flowing through that line. That's just to protect your copper, to make sure that you're not putting too much power through the certain gauge wire that you're running. These protect against the actual circuit. They detect how much power is coming in and how much power is going out and how much power is returning. So these make sure that everything is safe too. They don't just make sure how much power is going out. They detect how much is coming out and how much is coming back in, to detect if any power is being lost anywhere and to find an unsafe circuit. That's what those are for. And as of 2008, I believe, these are actually a requirement in all new homes that are built. So they do prevent many fires and save many lives. These are very, very nice circuit breakers, and they're very, how do I say, I don't know. They're a great piece of technology. Alright guys, so one last thing I gotta go ahead and explain is the difference between the neutral line and the hot line. The neutral line and the hot line. The neutral line and the ground line here, okay? So, there really is no difference. You can say there is a difference, and some people will say there's not. If you're taking a test for an electrician to become an electrician, there's going to be a big difference. They're going to act like they're worlds apart. Really, they're the same thing. So let's explain. We already explained what neutral is, okay? So this is actually coming from your transformer tap from your power company, and this is going to be where all your power flows back through from these hot lines, okay? The ground is just 100% a safety measure, okay? Houses built like back in the 1920s and crap didn't have this ground line. Houses built in old houses didn't have these. They only had two prong outlets. And even today, some appliances don't use a ground. The ground is not required for stuff to run, okay? It's just a safety measure, that's all it is. Can you guys hear the rain outside? That's crazy. It's actually like really hot outside. It's like a summer day. It's actually a summer night, but it's been really hot, and it's raining, and it just started raining out of nowhere. It's crazy. But yeah, just so you guys know what the hell that sound is. But anyways, okay. Ground is just a safety measure, okay? So to explain what it is, basically the Earth has this wonderful, characteristic to it, if you will, to absorb electricity. So basically, if you had a hotline, one of these hotlines, and you touched it, and you were touching the ground, literally, I mean the ground, if your feet were on the ground, this would shock the shit out of you. This would shock your balls off, okay? The reason is because the power will flow through you into the ground, because the ground absorbs electricity. Naturally, it just does. So you would be relative to ground, and this would shock you. But if you were magically floating in the air for some, I don't know how, but if you started floating in the air, you could touch this, you could lick it, you could make out with it all day, this bus bar is not going to shock you, okay? The second you touch ground, it'll shock you. Now, I don't want you guys to go home and try this like an experiment and stand on a piece of plywood and be like, oh, I'm not touching the ground, I'm touching this piece of plywood, because it'll still shock you. But that's why when linemen and stuff go working on live lines, they're actually suspended in the air, floating from like a helicopter or something. Then they're not actually touching the ground. That's how they can touch these huge hot lines and not get shocked. But those are typically like 500,000 volts. This is 200 or 120 volts. This was still way more than enough to kill you. It's the amps that kill you, not the volts. But I know some people say that's not true, because you do have to have a certain amount of volts to kill you, or to push the current through you to kill you. But anyways, the grounded terminal is literally just a huge piece of copper that goes into the ground. It goes into a huge piece of rebar, typically, and it just is stuck like 7 foot in the ground, and it's so that current can flow through the ground, okay? To put it simple. So it's basically, the idea behind it is, okay, if there is, let's just say, a metal appliance. Let's just say we have a light, okay? You have a lamp in your house, okay? Now let's just say for some reason little Johnny went over and knocked the light over, okay? The light was knocked off the table, and it knocked one of the wires in it loose. It knocked the hot wire loose, okay? Now the light was made out of metal. Okay, the little light that Johnny knocked over is made out of metal, so the wire that came loose is now touching the light, okay? The light that is made out of metal. Okay, so you go to pick it up because little Johnny knocked it over, and this hot line is touching the light, which is made out of metal, and you go to grab that thing, and you're grounded, you're screwed. It's going to shock you, and your muscles will contract, and you won't be able to let go of it, and you're dead, okay? But if it had a ground wire going to it, that ground wire would be attached to the frame of the light. Anything that's typically anything that's metal that's going to plug into your house has a ground wire attached to it. That way, if one of the wires in it does come loose, or something happens to where a hot wire touches the case of the appliance, if you go up to it and you touch it, it's not going to shock you, because the case is grounded, which means all that current that would have gone through your body is actually going to go through this ground wire first, because it has a lower resistance, and it's going to go into the ground. Typically, that'll pull so much current that it'll blow your 20 amp breaker, or whatever breaker size breaker you have. So it's actually going to flow back, and it's going to trip your circuit breaker. But that's better than you going and picking up the appliance yourself without a ground and it shocking you and killing you. Okay, so that's what the ground does. Now, the current can flow through the ground or the neutral just as easily. Normally it's supposed to flow through the neutral. In emergency cases, like I showed you when a little Johnny knocked the light over, it's going to flow through the ground. Okay. Now actually they are two separate wires, but when it comes to, like I said, it varies. I don't know if I said this to you guys yet, but it does vary from place to place. In the United States and different countries, everywhere has their own thing. And why they do it, I don't know. But here in California, in the United States, where I am, in your main panel, in a main panel that comes into your house, where your main feed comes in, your ground and your neutrals are on the same bus bar. So they are the exact same wires. They're actually bonded together on the same little terminal strip here. So your ground wires and your neutral wires will both go to this strip. Okay, and then that's what this little thing is here. This is huge thing is for your neutral wire. This is for your ground wire there. Okay, that's if this is a main panel. If this is coming in from your main transformer, they're the same wires. If this is a sub panel, they're kept separately. You notice that this neutral is not actually tied to the case of this panel. And this panel has to be grounded. So if one of these hot wires came loose and touched the case of this panel, and I were to go grab this panel to open it up, it's going to shock me. But if it's grounded, the current is going to flow through the ground and it's not going to shock me, right? But this neutral is not tied to the case of this panel. If this is a main panel, you're going to have your ground terminal coming in there, you're going to have your ground wire going in there, you're going to have your neutral going in there, so the same thing, and you're going to have a screw that goes in through there, and it's going to actually tie this neutral and ground, which are together, to the case of this to make this case grounded. In this case, I was using it as a sub panel, which means all the neutrals are floating, okay? None of them are touching the ground. So I didn't have that screw going there. I didn't put my ground wire in there. I put my ground wire in here. It's grounded to the case. The neutrals are all separated from the grounds. The grounds and the neutrals are not touching. Okay, they're totally separate. That's how it is in California. Sub panels are separate, main panels all the same. You don't have to have a ground strip on the side, you don't have to have this crap. It's all the same. Why they do that? It's weird. I don't know. What's weird is in the main panel where the feeds come in, they have the neutrals and the grounds tied together, but in the sub panel they have to be separated. Even though the source that they're getting it from is the main panel where they are tied together, they have to be separated in a sub panel. So I don't know if it makes any sense to you guys, but basically in a sub panel they're separated. Main panel, they can be tied together. They're all the same. Grounds and neutrals are the same. They serve the same purpose. Like I said, ground is for safety, neutrals for where current normally flows through, but they do the exact same thing. It's just that the ground is tied to the case of your appliance typically. So that's what that's the deal with the grounds and neutrals. Alright guys, so one more thing I just wanted to cover, just so you guys know. I mean, definitely don't go into this type of stuff if you don't feel confident, okay? You gotta know what you're doing. I mean, it's really, really simple. It's very simple once you kind of understand it. All it is you have two hot lines. Those are the guys you want to watch out for. Your neutral line, and then these are all your circuits. So you want to add a circuit to your house. You get a breaker, right? Okay. You have your hot lines there, so your power is going to come out of here, and then you can run it to your circuit. Now, like I said, this isn't like a full-blown tutorial or anything. You're going to have to know stuff like wire gauges. 60 amp breaker, you're going to need number 6 wiring, okay? 20 amp breaker, number 12 wiring. Don't go in your breaker box and saying, man, that 15 amp breaker trips all the time, so I'm going to go ahead and pop a 20 in there. There's reasons why there's 15 amp and 20 amp breakers, okay? You have to know the wire gauges, you have to know all that stuff. Yes, I know all that stuff, but this is not a tutorial on that, and that would go forever if I showed you guys how to wire all that crap up. But it's really simple once you guys understand it. I mean, just do your basic research, but definitely don't go screwing around in here if you're not confident, especially in a main panel box, because you cannot shut off the electricity, okay? So that's another thing I want to show you guys real quick, is that if you guys are messing around in your main panel, I mean, I'm not gonna lie, I don't turn the main breaker off because I'm careful, and I've done it so many times that I'm confident in it, and I know what I'm doing, and I know what not to touch and what to touch. Okay, but I encourage you guys to turn your main breaker off, no matter what the case is. Now, in some cases, in a lot of homes, and I know in our house, our main breaker is like this. Okay, it looks just like a typical circuit breaker. It's not a panel like this. It doesn't have a big breaker at the top. It's just a panel with a bunch of switches in line, right? And your breaker is just going to be one like that. It's 100 amp, 125 amp, something like that. So it looks like a normal circuit breaker. And it'll be labeled main, principal, main breaker, whatever, right? So you'll know it's the main circuit breaker. But it actually feeds in through the bus bar. That's the only breaker that works backwards, okay? Like I said, normally your power comes in to your breaker from these teeth and goes out through that screw. And your main breaker, if you have a main breaker like this, your power will come in through these screws and it'll enter your bus bar through here. So this will supply power to your entire bus bar. So you guys get what I'm saying? This would be your main breaker. Your power would come in here from your transformer, your service feed, and it would when you have this on, or when you have it on like that, it would put in power through those little terminals right there. So you'd have your 120 leg and your 120 leg. And there wouldn't be like a big breaker up here or anything. This would just supply power, and then all your other breakers would tap off that. But one thing I want to make clear, no matter what kind of a setup you have, whether you have a main breaker like this or like this, these are very common. In larger homes it's like this, smaller homes like this. This feed will never shut off. Okay, no matter what. If this breaker is on or off, no matter what way it's flipped, no matter if it's tripped, it doesn't matter what the heck's going on. These are always going to be live, okay? Because it's a light. It's basically like a huge fancy ass light switch. Okay, it's going to shut off the power on this side. These, I mean, I don't want to say your panel's ever safe. Okay, don't ever assume anything's safe. Okay, but like I said, I encourage you to flip off your main breaker. But even if you flip off your main breaker, all this is safe. Now this is a lot of space. This is a lot of surface area to be careful for when you're working in here. So that's why I encourage you to shut this off. You don't ever want any metal objects to touch this and then touch the panel. You'll have an arc flash like you've never seen before, okay? But I mean, this is a lot of surface area of live energized connectors. So that's why I say turn off your main breaker. But even when you turn off your main breaker, these lugs here, these huge lugs, are not going to shut off, because this breaker does not shut off what comes into it, only what goes out of it. Okay. Same thing for like one of these guys. If it looks like, a little breaker like this, those little screw terminals, what is coming into those, if it's a main breaker, what's going into those, you will never shut those screws off. Okay, those screws will never shut off. Doesn't matter what way this switch is flipped, no matter what the hell's going on this side, there's nothing you can do to shut off those screw terminals. So you want to be very careful. Those will shock you. They have the potential to kill you. If you're working on something and a tool touches that and it touches the case of this, there is no main breaker to trip. There's nothing going on. You're going for a ride, man. The thing's gonna shock. It's gonna have a huge arc flash, and that's how fires happen. That's how people get seriously injured, because what's coming through those lines is, it can be thousands of amps. Who knows? God knows the size of the breaker at the transformer pad down the street where the power is coming from. So, I mean, don't ever, you guys got to be very careful when you're dealing with main panels. Sub panels, you can just shut off the panel and everything's off, okay? But a main panel where your feed's coming in, you got to be careful. You got to know what you're doing. One way you can shut off the panel, which I'm not going to encourage you guys to do, is you can pull out your meter. If you pull out your meter, it will shut off your entire panel, but of course, the feeds that are coming into the meter, those can't be shut off. But you do have to have, the meter's technically not your property, it's the electric companies, and you shouldn't be dicking around with your meter unless you know what you're doing, and you do have to cut seals and stuff on there to do that. And if your electric company comes by and sees that you cut your seal, they're going to have suspicions that you're stealing power. So I don't encourage you guys to do that, but that is a way to shut off the power to your panel. If it is an emergency situation and something is going on with your main terminals, by all means, cut the seal on your meter and rip that damn thing out of there. You just pull it straight out, and that'll shut off the power to your panel. But I just want to let you guys know that there is no way to shut off the feeds going into your panel besides to call your power company and tell them to shut the power off. But you have to be like an electrician to do that. You can't just tell them, hey, I'm working on some power here. They're not going to let you do it. You have to be a certified electrician to tell them that you're going to pull out the meter and you want to shut off the power and everything. So I just want to let you guys know that, that is some serious stuff there. You cannot shut that off ever in any situation, and that does have a lot of power and a lot of potential going through it. So, I mean, it's pretty basic once you guys understand it all. It's, not too hard. Just how it's all wired up. It's very simple. It looks complicated. When you pull the cover off, there will be a million wires in here, and your jaw will drop, and you'll be like, what the hell? But really, it's just a bunch of hot wires coming from the breakers, a bunch of circuits going to the neutral bars, a bunch of ground wires, just a bunch of repetitive stuff. If you break it down, it's a bunch of single circuits. They're all simple. It's just a bunch of stuff clumped into one space, and that's why it looks so complicated. But it's really not too complicated. Like I said, guys, don't go in here and screw around with stuff if you don't know what you're doing, because you do have to kind of be confident in your work. And if you don't know what you're doing, you can get hurt, you can start a fire, you can start some serious stuff. But if you do know what you're doing, you can save a lot of money, you can fix simple problems, simple issues, and it's just, a lot nicer to know what the hell's going on inside stuff like this. But I mean, that's pretty much it, just for the basic rundown of the electric panel and power distribution and stuff like that for your guys' home or whatever the heck you guys are doing this for. But I hope you guys enjoyed this. I might do further, discussion or tutorials or whatever on this, but that's it for this one, guys. And as always, have a good one.